We're going to start trying to figure out how to identify where maximum and minimum points are for a graph. And to do that, we need to understand something called critical numbers. Critical numbers. So we're just going to give the definition of what critical numbers are, and we'll draw some illustrations of how they might be useful, and then we'll do some examples algebraically of finding some critical numbers for particular functions. So let's start with a critical number. So C, let's call it C. C is a critical number. C is a critical number of the function f if one of two things happens. If f prime of C equals 0, or f prime of C does not exist. Okay? So one of two things. Now remember what this means. If f prime of C is 0, that means that f, the function f, has a tangent line slope of 0 at C. All right? So if we're looking at f prime of C equaling 0, let's visualize kind of what that looks like. So let's say that C is right here. If f prime of C equals 0, then you may have a point like this where you have a horizontal tangent line, and in this case you'd have at least a local maximum or a relative maximum at C. Similarly, you could have a relative minimum. You could have a relative minimum at C. So here's C. You could have something like this, where you have a relative minimum, but you're not guaranteed to have a relative max or min if your tangent line slope is 0. Keep drawing a vertical line. Sorry about that. So you could have something like this, where your graph comes up, goes horizontal, and then goes up again after. And at this point, we have neither a max nor a min. Okay? You could also have maybe a more obvious case where you just have a horizontal line. So in fact, at this point, you have a horizontal line. And I suppose technically this could be called a relative maximum or a relative minimum because it's less than or equal to all the nearby y values, and it's greater than or equal to all the nearby y values. But these are kind of the more unusual cases, but they just go to show that if the derivative is 0, that doesn't necessarily mean you have a maximum or a minimum. But it could be useful to help us locate a maximum or a minimum. Okay? So let's look at cases where f prime of C does not exist, so we can imagine some possibilities there. So if f prime of C does not exist, well, one reason f prime of C may not exist is because perhaps the function is not even defined at C. Maybe, you could have an asymptote, and so your graph does this kind of thing near C. The function may not be defined anywhere near C, and it may stop short of C on both sides, right? So it's not even defined on either side of C or at C itself. It may not be differentiable at C. It won't be differentiable at C if you have a sharp point at C. But in this case, you have a relative maximum at C. Similarly, you could have a relative minimum at C if you had a sharp point at the bottom. You could have, the function could be defined at C, but it could be discontinuous like this. So that's not differentiable either. And you can see here that we have a relative maximum at C also, which is slightly different than this case. So there are examples where the derivative equals 0. There are examples where the derivative does not even exist. And the reason we call these critical numbers is because if you have a relative minimum or maximum, they have to occur at a critical number. So that's kind of key. So the importance of critical numbers is that that's where relative max or min values have to occur. So we might call that a theorem. a theorem that says if a function has a relative min or max, it has to occur at a critical number. Okay? And it really is important that you're talking about a relative min or max, not an absolute min or max. So that'll be addressed in a different video. Remember, on an absolute min or max, you don't have to be defined on both sides of the C value, whereas on a relative min or max, you do. So if you're going to have a relative min or max, the best place to look is at your critical numbers. Now, that doesn't guarantee that you're going to have a relative min or max just because it's a critical number. We saw several cases, right, where we had critical numbers that didn't yield a relative min or max. But if you're going to, they're going to happen at the critical numbers, all right? So this is the importance of critical numbers. This is why we're interested in them. But now let's practice some of the algebra in actually finding critical numbers. Okay? So let's say, we'll label these as examples. Find the critical numbers. If you have any, you're not guaranteed to have any, okay? You might have a function that the derivative exists everywhere, and none of the derivatives are equal to 0, okay? So let's see, so we'll call this example 1, and let's look at the function f of x equals, how about 3x cubed minus 4x squared plus 9. Just plus 9x. Just a basic polynomial, cubic polynomial function. And so we need to, for critical numbers, we need to find the derivative so that we can figure out where the derivative equals 0 and where it does not exist. So what we need to do first is find the derivative. So f prime of x equals 9x squared minus 8x plus 9. Okay, so no problem there. So we need to look at two things now. Most students remember to look at where the derivative equals 0. Okay, but you also have to check to see where the derivative doesn't exist. So we'll keep that in mind. Now in this case, we want to figure out where this trinomial equals 0. So where does this guy equal 0? We need to solve this equation for x. And so you might try factoring or something, but I think the quickest way to do this is going to be with the quadratic formula, because this is a quadratic or degree 2 equation. So x equals negative b, so that's positive 8, plus or minus the square root of b squared, that's 64, minus 4 times a times c. A times c is 81, so 4 times 81. All of that over 2 times a, which is 18, okay? And so what we see here is if we look just under the square root, 4 times 81 is bigger than 64, okay? Bigger than 64, meaning that if I take 64 minus this number, I'll get a negative. And if I take the square root of that, what I'm going to get is an imaginary number. And so there are no real numbers for which, there's no real number x values for which f prime of x equals 0. So there are no x values here. So we don't have any critical numbers yet, because the only x values that make this true are imaginary, and we're not interested in those. Now, let's look at f prime of x and where it does not exist. And basically what we do is we look at the f prime of x formula and we ask about the domain. Are there any x values for which you cannot calculate this formula? And the answer is no. You can plug any x value into this formula and get a number. So f prime of x exists everywhere. Meaning that we get no x values here that make f prime of x not exist. So what we see in this particular example is this particular function f of x has no critical numbers, which means that there is not a relative minimum or a relative maximum of this function. Okay? So that's pretty interesting. We can gather that from the fact that it has no critical numbers. So that's an interesting case. You're not guaranteed to have any critical numbers, and here's a case where that happens. Let's look at another example. Example 2. So that was a polynomial example. So let's see, what else would be interesting? Let's look at f of x equals the cube root of x squared minus 9. Okay? So if we want the derivative of this, it's useful to first think of this cube root as an exponent. So it's the same thing as x squared minus 9 to the 1/3 power. And now the derivative isn't too bad. So f prime of x equals, applying the power rule, we get 1/3 times x squared minus 9 to the negative 2/3. And then we have to use the chain rule and multiply by the derivative of what's inside. So the derivative of x squared is 2x minus the derivative of 9. Well, that's 0. So this just turns out to be 2x. And if we clean this up a little bit, f prime of x equals, we can turn it into a fraction. So the 2x times 1 is 2x on top. And on the bottom we have 3 times x squared minus 9. This was a negative exponent, so I can put it on the bottom and make it positive 2/3. Okay? And so now this is maybe as simple as this particular derivative gets. So let's look at where f prime of x equals 0. Where does this fraction equal 0? Well, for a fraction to equal 0, the numerator has to be 0. So in this case, we want to know where 2x equals 0. And if we solve that for x, we get a critical number of 0. So what does that tell us? That tells us that if x is 0, the derivative of the function is 0. In other words, if x is 0, this function has a horizontal tangent line. This original function has a horizontal tangent line. So that's a critical number. 0 is a critical number. It might be the location of a relative minimum or maximum. And we're not going to explore whether it is or is not in this particular video. We'll look more at that later on. Right now we're just exploring how to find critical numbers and why they're important. Okay? Now let's look at, we always forget the second part, let's look at where f prime of x does not exist. So in other words, when will this fraction not exist? And when does a fraction not exist? Well, a fraction doesn't exist. It doesn't output anything if the denominator is 0. The only way that this guy could be 0 is if x squared minus 9 were 0. That's the only variable part of the equation. So we need to know where x squared minus 9 equals 0. So we solve this for x, and we get two answers, plus or minus 3. So now the derivative of this function does not exist if x is 3 or negative 3. And so that could be for many reasons. It could be because you have a vertical tangent line, right? Remember, a vertical tangent line means the function is not differentiable. It could be a sharp point or something like that. Or it may not even be defined. In fact, this function is defined everywhere, right? It's a cube root, so its domain is all real numbers. It's continuous everywhere as well. Actually, because of the x squared, you might have a sharp point on this graph. So that may be why it's not differentiable at plus or minus 3. You could play around with that to kind of visualize what's happening. But the critical numbers, as far as we're concerned right now, the critical numbers are 0, -3, and +3. Those are the candidates for where we may potentially have relative minimum or maximum points for this graph, okay? So we did a polynomial, we did a cube root. There's no way I can do all the different possible examples. One of the troubles with doing this type of question is you could encounter any algebra that you've learned, okay? So it's important for you to practice a bunch, do as many problems as possible, so that you can refine any algebra skills that are lacking, okay? But I'm just trying to do a variety of examples here so you can see different applications of the concept of critical numbers. So let's look at another function. Let's look at something involving a trig function, let's say. So let's say we have f of x equals tangent of x minus 4x, okay? And so in this case, if we want to differentiate to find the critical numbers, f prime of x will be the derivative of tangent of x is secant squared of x, minus the derivative of 4x is 4. And that's about as simple as that gets. So now we have to solve the equation where that derivative equals 0. Okay? So we need to know where secant squared of x minus 4 equals 0. So we add 4 to both sides. In fact, it may be easier to think of secant squared as its reciprocal, 1 over cosine squared, because we're more familiar with the cosine values. So now I've got 1 over cosine squared, so I could flip both sides, right? 4 is the same thing as 4 over 1, so I'll flip that side as well. And so I get cosine squared of x equals 1/4. If I come up here, because I'm running out of room, now I'm going to take the square root of both sides. So cosine of x equals plus or minus 1/2. The square root of 1/4 is 1/2. So I need to figure out all the x values, because I'm trying to solve for x, for which cosine of x equals 1/2 or -1/2. So I'm going to have to draw a picture to imagine what's going on here. So in this case, we're looking for radian measures because cosine of angles equal these ratios. So cosine is the horizontal measurement in your unit circle or your coordinate plane. So if I'm looking for a horizontal measurement of 1/2, then I could be looking at this triangle or I could be looking at this triangle. Both of these are 30, 60, 90 triangles where the reference angle is 60 degrees. So this angle is 60 degrees in terms of radians, which is pi over 3. And this guy is just shy of 2 pi, so this is 5 pi over 3. Okay? I could also look at where cosine is -1/2. And so that would yield a triangle over here and a triangle down here. Again, with a reference angle of 60 degrees or pi over 3. So this would be 2 pi over 3. And this would be 3 pi over 3, 4 pi over 3. Okay? So all of these angles, all of these x values will make this true. And I could continue rotating forever and get an infinite number of angles that land at each of these places. Infinite number of coterminal angles. So x could be pi over 3, or any other angle that lands in the same place. So we typically write that as plus 2k pi. In other words, we're taking multiples where k is an integer of 2 pi, because one revolution of the circle is 2 pi radians, so we could just keep adding 2 pi. But we can make it a little bit better because the angles over here are a rotation of pi away. So I could knock out both of these, all of the angles that land in either of those places, by saying pi over 3 plus k pi, multiples of pi instead. And that knocks out both of those. So I'll circle those because those are circled. Similarly, I could say, let me put this in a box, I could say x could be 2 pi over 3 And then all the angles that land here and here are separated by a pi rotation. So I could say plus k pi there as well. Okay? So this function has an infinite number of critical values, critical points, critical numbers, sorry. They have different names, but critical numbers is what we're going to call them here. So an infinite number of critical numbers. And again, k here is an element of the integers, which we write as this fancy z. Again, the way I drew that was, did the top half of my z, then I came up here and mirror image that in parallel to that diagonal. Okay? So k is an integer. So those are critical numbers of this blue function, tangent of x minus 4x. But we still need to explore where the derivative does not exist. So let's do that next. Let's give us a fresh space here. Where does this particular derivative not exist? Oftentimes, when you're asking where something doesn't exist, you're looking for denominators, right? Or if you have square roots, we know that there are issues with square roots or logarithms, things like that. But in this case, secant squared is 1 over cosine. So this function, this derivative, won't exist. It will not exist if the denominator, cosine of x, is 0. Okay? So if 1 over cosine does not exist, that means cosine has to be 0. And so now we do the same analysis to find the x values for which cosine equals 0. Again, cosine is the horizontal measurement. So I know I have a 0 horizontal measurement. In other words, I'm going to land, my angle is going to land on the y-axis, either at the top or the bottom. And of course, this is the angle pi over 2, and this is the angle 3 pi over 2. And once again, those two angles are separated perfectly by a rotation of pi radians. So the x values, or the angles that come out of this, are pi over 2 plus k pi, where k is an integer. So all of our critical numbers are, we have an infinite number of critical numbers for which the derivative doesn't exist. We have an infinite number of critical numbers where the derivative is 0. I'm just summarizing here all of the critical numbers. So any of these x's, all of these x's are the critical numbers, okay? For this particular arithmetic of the tangent and polynomial function 4x.